We're now going to focus our attention on hard problems. Here's a list of a few different hard problems. The vertex cover, the knapsack problem, and even our main paradigm of solving problems in integer programming is a hard problem. We're going to be interested in effectively three things about hard problems. First, identifying what it is to be a hard problem. Second, identifying how to show that a particular problem is hard or easy. And third, given that we know a problem is hard, how do we actually deal with it? The core hard problem that we're going to be discussing is the 3-SAT problem. The 3-SAT problem exhibits a lot of the features of many hard problems. And we'll see that many problems can be reduced to 3-SAT, or rather 3-SAT can be reduced to them. In the 3-SAT problem, we're given a collection of literals. Here our literals are the x's. X's are just variables that can take on either the value true or false. We also have negated literals. In this case, bar x2 is the opposite of whatever value we've assigned to x2. If x2 is true, then x2 bar is false. In addition to all these literals, we're also going to be given a series of clauses. A clause contains 3 literals, and it's true only when at least one of the literals inside of the clause is true. So, for example, if we have the clause that includes x1, x2 bar, and x3, this clause is true only if x1 is set to true, x2 is set to false, or x3 is set to true. Here, x2 has to be set to false because x2 bar is the literal that's contained inside of this clause. In general, we're going to think of clauses as functions on the literals. So in this case, clause 1 is the function of all of the literals, and it's set to the value true only when x1 is true, x2 is false, or x3 is true. So a clause is a function from literals to truth values. The way we interpret these little symbols is this upward facing V is an OR symbol, signifying that this clause is going to be true when x1 or x2 or x3 is set to true. The 3 in the 3-SAT comes from the fact that every clause has exactly 3 literals in it. The 3-SAT problem, then, includes an input that consists of a set of literals, xi, and a set of clauses, cj, that evaluate according to how the literals are assigned truth values. Because it's a 3-SAT problem, each of these clauses contains exactly 3 literals. Now we can understand what 3-SAT actually stands for. It's the 3 satisfiability problem. The idea is that this is a decision problem, and we'd like to output the answer yes if all of these clauses can be satisfied. That is, we can find a consistent assignment of the literals so that all the clauses evaluate to true. Otherwise, we output the value no. To get a better idea of the 3-SAT problem, we can model it as an integer program. In this case, our integer program is going to have a variable yj for every clause j, and a variable xi for every literal I. We set the value of yj as high as we can, but we're restricted by the values of the literals. Specifically, at least one of the literals in the clause j has to be set to true. We break the literals into 2 components: the literals that aren't negated, lj, and the literals that are negated, nj. Among the literals that are negated, we take 1 minus the value that it's assigned to, xi, and sum over all of them. For the literals that aren't negated, we sum over all of them without any sort of subtraction. In total, if this quantity is greater than or equal to 1, we know that one of the literals inside of the clause j is set to true, and so we set the value of yj to true. Because this is a maximization problem, we'll take the largest value of yj we can, which, if one of the literals is true, is equal to 1. We set the value of our 3-SAT problem equal to yes if the value of this integer program is equal to n. We're going to see the three-set problem quite frequently when we talk about hard problems because it sort of forms a quintessential hard problem that we'd like to study. Before we do study the three-set problem or any others, we'd like to get an idea of what hard actually means. To build some notation, we'll call a problem P, and we'll identify as the set I all of the instances of the problem P. Remember that an instance is effectively an input. I contains all possible inputs we can have to the problem P. We're interested in designing algorithms for our problem, and in this case an algorithm is some function that takes as its input an instance and outputs some solution. A hard problem is defined by a problem where some algorithm doesn't exist. Specifically, if a problem is hard, we can't find any algorithm so that two conditions are true. The first condition is that for every instance, this algorithm has to output the optimal solution, and second, for every instance, this algorithm has to run in polynomial time. There is no algorithm for a hard problem that satisfies both of these conditions. This is what it means to be hard. A key component of this hardness is the running time of our algorithm. Specifically, we are prevented from writing any polynomial time algorithm for a hard problem. Remember, polynomial time is defined in terms of big O notation, and it's big O of n to the k. Here, n is the problem size, and k is some constant. Occasionally, when we analyze algorithms, the polynomial time can actually look a little bit different, and we can have 2 to the log n. You can see that in this case, the log and the 2 are going to cancel each other out, and this is actually a polynomial time runtime. On the other hand, there's quite a few runtimes over here that aren't polynomial. Anytime n is in an exponent of an expression, except for this one particular case, we have a non-polynomial time runtime. Of particular note is a runtime that depends on C, where C is some number. We've seen in dynamic programming that we can have a knapsack algorithm written as a dynamic program that runs in order C to the n time, where C is the size of the knapsack. This type of algorithm is not a polynomial time algorithm. The reason why is a little detailed, and we won't get into it. For now, throughout this class, we're just going to exclude any type of runtime that depends on a particular input number of our problem.